Raymond and David are in the house. Good morning.
Hey, good morning.
Hello.
Let's see. $7.3. There we are. Marvelous. Well, it is 8 o'clock and you are all here as you are supposed to be. So let's get after it. Today's lesson hung in the balance because I went riding in the steeps out behind my house this morning on my mountain bike. And one of these days, I'm just going to be laying out there in the dirt, injured.
No, you got it.
Not today. Yes. Cool. Let's see. We got all kinds of stuff to consider. All right. 7.3. My computer starts out asleep, I see. So, properties of the Laplace transform. Are you practicing your cursive L so that you can do this beautifully? So one of the things you will see maybe in the book, if you read it, there's a number of ways to kind of write this stuff down, and it can seem rather confusing sometimes. But if I said something like, this was a function of t that we were initially taking the Laplace transfer of, then what you learned yesterday is that it's going to pop back out as some new function. Notice I used capital F because the function has changed. It's still f for function, but it's capital F just because it's different than little f, but it still means function. But of course, now we're in some new world. We're in the letter S now. And again, you can make a whole bunch of this if you take more advanced differential equation courses, but for us, it really doesn't even make any difference. We're going to change it into this world of S, and then we're going to change it back into the world of T. And so in one sense, it doesn't even matter what S means. Although I said yesterday, the most popular use of it is to change it from the land of time to the land of frequency. Couple of things we learned yesterday that I just want to formalize a little bit, since this section is technically about some of the properties of Laplace transforms, but this is one of them we learned yesterday. We said, hey, if you have a Laplace transform of some constant times this function of t, that's going to be the same as just pulling the constant out in front. In other words, you can just kind of ignore the constant and worry about but my question to you is, can you explain that? Like, why is that true? Why is that not just some theorem that I would write down from a book? Why can you say, well, yeah, that makes perfect sense? Can you explain that to yourself, to somebody else? Why would that be true? Somebody take a stab at it, even if you're wrong, that's fine.
Well, you can do that with integrals, and if you were to leave the constant in there, it'd be the same.
Yeah, that's exactly right. Like, don't forget a Laplace transform is just kind of a cool integral, right? So if I was looking at this one, when I say, well, the definition of Laplace transform of junk is take the junk and multiply it mysteriously by this little statement and take its integral. So the reality is it's an integral, right? And so we know that the integral, if there's a constant there, we can pull the constant out front. So in a sense, you should say, yeah, of course that makes sense. So we're going to need to know that later on. That's really an important thing. For instance, we saw yesterday that the Laplace transform of 1 was actually 1 over s, turns 1s into 1 over s's in this new land. And so I'll even show you this today because I want to make sure you get a chance to see this before the weekend. What if you were going the other direction and you had not 1 over s, but you had 4 over s, and you were actually trying to go back the other direction to the Laplace transform of something? So it's kind of like, what's the, I guess, mathematicians, or we would call this the inverse Laplace transform, because we're going to need to do that. If we went the other way, well, you'd say, well, darn it, that would work, except for it's 1 over s, and that's a 4. So the fact that you can just take the 4 out, in other words, you can think of this as 4 times 1 over s, that just means, oh, okay, that'd be the Laplace transform of 1 with a 4 in front of it. So really, that'd be the Laplace transform of 4. And so that constant business is really important. We saw yesterday that a number of our Laplace transforms had, let's look at my table. A whole bunch of them had 1s on top. Bam, bam, bam. And certain values. And so we need a 1 up there. Well, if there happened to be a 7 up there, no problem. You can just pull that 7 out. Or over here, something that I'll talk about today. You know, this is sort of saying that whatever is sitting here, it's got to also be sitting there. Like if that's a 5, then this has got to be a 5 squared or 25. Like you can't mess with that. Well, what if this isn't a 5? What if it's a 6? Well, we're going to actually be able to multiply that thing by a constant and kind of make it what we want it to be. And so again, you don't need to understand that completely yet, but just the concept that a constant can be pulled out, since really a Laplace transform is just an integral, and no problem, it works. So I want to start off with something kind of cool. Dang, computers went black again. Give it a second to wake up. So I want to write this down formally. Like yesterday we said, if you had, just to write it down, but we said we don't mind plus signs. Like if you have 2 functions that are added together and you needed to play the Laplace transform of them. And again, you should understand where that's going, because didn't we have that on the test you just took? It was like sine of 85t and it was plus t squared or something like that. Well, you say, okay, well, that's no problem. Since Laplace transform is an integral, and integrals and derivatives like plus signs, then you would say, yeah, it's no problem. You can just split those into 2 parts and kind of do them separately. So I don't have to come up with some crazy example or crazy way to kind of work that. Again, just because it's an integral. So those are a couple of properties we looked at yesterday. But now I want to show you just one thing kind of quick. You should agree that this isn't looking good. This is the one I just showed you a second ago on your sheet, but you should say, well, that's not going to be very fun. Because we're going to have to take the integral of that. But didn't we learn yesterday? Let's see. What was yesterday's conclusion about the Laplace transform? Let's see, let's write a couple of things down. One of them was, what's the Laplace transform of e to the at? We said that was 1 over s minus a. And I won't rewrite this, but it was important that s be bigger than a. And again, what's interesting for us is that isn't really going to matter that much, because we're going to take the s back out of it anyway. but we said that was true. And then right before we left, we saw, which was really terrifying, did we not, that the Laplace transform of the sine of bt, which I don't remember. We went to a lot of trouble to make that. You probably did that in your assignment last night, but we said, and I used a different letter here, but it was a over s squared plus a squared. So since I wrote b there, it'd be b over b squared plus s squared. So I want you to think about this for a second. Is there any, like, we sort of know them individually, but we don't know them collectively. Now, again, there's no plus sign right here. If there was, then I would just say, great, it's those two added together. It'd be really simple, but it's not a plus sign. Those are multiplied. So is there any help? Is there anything, is it any help that we sort of know them individually in order to find them put together? Now, again, I say this because in our Laplace, or in our, that wasn't the right one, in our set of notes, did I throw those away from last section? So I'll have to get them back. On the last test, or in that last section, we had in our rules for solving second order differential equations, it was not uncommon for us to have something on the other side of the equal sign that looked like that, right? I mean, didn't we have kind of a way of handling it if there happened to be something, ugly like that over there? But again, what's cool about Laplace transforms is that was one of, well, sort of three different options. Like if it's equal to 0, do this. If it's equal to t's and e's, do this. If it's got trig in it, do this. And we had all these different methods. But it is possible that something as ugly as e alpha t cosine of theta t, it's something like that is on the other side of the equal sign, right? That's not impossible. And so, that's what's sitting here. What if you had an e 5t sine of 4t on the other side? Well, if we're going to take the Laplace transform of both sides, we got to be able to take the Laplace transform of that. But what is it any help that we sort of know there are two answers individually? That's the question I want you to think about for a second. And to give you something to think about, would you agree that at least to write out what the Laplace transform is, Laplace transform was always just, well, whatever this function is right here, if I just rewrite it, we always took the function and then we said, all right, now that gets multiplied by e to the negative st. And then we evaluate it from infinity to 0. And, but you should look at this and go, that's going to not be all that fun. Because now it's got three things, right? So your thought should be, oh boy, that's not good. But what can we do algebraically to make that a little less troublesome?
You can combine the e's, right?
Yeah, can't you put those e's together? Would you agree that would then be the same thing as e to the, well, you add exponents, so that'd be at minus st, right? At minus st, or a minus s times t. So now it only has two. But yesterday, didn't we say with respect to this one here that it was, the same thing? It was like the sine of bt times e to the negative st. That's what it was, right? And we saw that when we had to do integration by parts twice to survive that, and it was really horrible. And yet it actually produced this answer, right? Well, what's the difference? Stare at this a little bit. What's the difference between these two these two arrangements?
Just a and the exponent.
Yeah, I mean, stare at this right here. They're identical, except for this one has an a minus s, and this one just has a minus s. And those are both constants anyway. So if that's true, then wouldn't I just be replacing, well, this negative s? Isn't that all I really have to do then?
Would you replace it with some other constant, or what are you going to replace it with?
Yeah, take a look at this. So I got to do a little bit of algebra work here to make this an acceptable move. But like yesterday, you may remember we said, well, in order for that to work right, we kind of need to take the negative out front. Remember how that negative was really important, because when we stuck infinity in there, it wasn't going to disappear without that being negative. So now there's a match there in the sense that I have a negative junk and negative junk. The only difference is one of them is s, one of them is s minus a. So here, when this was just sine of bt, then I got this as my answer. And we're saying up here with that extra e in it, since this had an e in it, whenever you have e to the junk that's a part of it, all you really have to do then is just switch out s for s minus a. In other words, the final conclusion of this is this statement right here. Is actually equal to this. Oops. Is equal to this, except for what? What do I need to change?
It's going to be b squared plus s minus a squared.
That's exactly right. All I have to do is switch s for s minus a, and then they're identical. That's kind of a cool trick, wouldn't you agree? Because otherwise I would have had to, do integration by parts. But think about it. Isn't this really the same problem as this once I combined them? As soon as I got them combined, they're really the same problem, right? So I would have went through the same exact process. The only difference is I would just replace s with s minus a. Now that turns out to be really a powerful statement in the sense that it's kind of true for anything. So let me even formalize that at a deeper level. If you have the Laplace transform, this is super powerful, and it'll come up as examples, and it'll deepen your understanding a little bit. But if you have e to the at times any function, doesn't even matter that it was sine. So a second ago it was sine, right? But it could have been cosine, or it could have been logarithm, or tangent, or anything we wanted it to be. T cubed, something like that. Any function, then what's going to happen? Well, at the top, I said, if you take the Laplace transform of some function, then you get a different function. That's very important, right? It's not the same function. In other words, back here, the original function was 1, and the new function was 1 over s. They're not the same function. Or here, did I write sine down? Here, I started with the Laplace transform of the sine of junk, and then I got a brand new equation over here that was a totally different equation. And yet, instead of a function of t, it was a function of s. Do you understand that that's what this statement up here means? This is just saying I started with one function that was based on t, and I got a brand new function. You were using the letter f just because f is function, except for now it's a function of s. And so what's true if you have e to the at times any function? You get a function out of s, except for thanks to that a there, it just changes the exponent. Whenever there used to be an s, now there's going to be an s minus a. You see that that's broader than just if that was sine? Do you understand what that statement means? So let's try that out. from yesterday as a powerful example. Like yesterday, didn't we figure out what the Laplace transform of t squared was? Now we didn't do that completely. But we said it was like something factorial over something. What I remember is, since that's t squared, this was always one higher power. I'll look at the sheet again with you. But it was like that was always one higher power. And then I think what was on top of this was 2 factorial. So 2 factorial is 2 times 1. So that's the Laplace transform of t squared. Let's go double check that. I know I'm right, but just slow down and let you think about it a little bit. Yeah, so n is 2 factorial, 2 plus 1. Yeah, 2 factorial over s cubed. Yeah, that's right. And so you know that. So what if I asked you, what's the Laplace transform of e to the 6t times t squared? Now you should agree that were I to have to do this traditionally, it would be like, oh no, the integral of e to the 6t times t squared times e to the negative st. And so I've got to do that integral, right? But again, the fact that e to the 6t and the e to the minus st are both the same terms means I could really put them together and only have one e. And so if that's the case, based on what I just said up here, do you know? Do you understand what that answer would be?
Is it 2 factorial over s minus a cubed?
Exactly. You replace s with s minus a. Any place you see s, you put s minus a instead. So I have s cubed, now it's s minus a cubed. And so yeah, 2 factorial. I guess I'll leave the factorial in it just because it kind of looks better. 2 factorial is 2 though, so it's kind of a weird one. So that means cool. So do you see the power of this? In other words, if you need to take the Laplace transform of something with an e in it, you should be like, yes, I can kind of ignore that. Like I don't even have to worry about it. Do you see the power of that? Again, we'll be doing examples so that'll have a chance to get into your soul a little bit more, but this is one of them that is really helpful.
So in this case, it would be s minus b though, right?
Yeah. Did I use b instead of? No, because I used a up there.
Oh, okay. I was looking down below. I thought I saw b, like the e. The
That's
b,
a 6. My 6s and b's look the same.
Oh, it's a 6. Oh, okay. So b.
So the key is whatever that is, whatever letter that is, it's whatever's with the e. Oh, I'm sorry. I see what you're getting at now. So Ben's right. I mean, this was an a up here, but didn't I choose a to be 6? And so he's exactly right. Thank you, Ben. I picked a to be 6. And so wouldn't this be x minus 6? He's right. Ben's exactly right. Thank you, Ben.
I've learned not to question Ben long ago. He's
Me
always
too.
right.
I know Ben's also, he thinks a lot before he speaks, which is a good quality. Okay, now we're really close. This entire section is supposed to just be about the properties of these, but I want to get to actually doing a problem today because it's just hard to do this in theory. I want to actually accomplish something, but we got to do something cool and potentially complicated. What about derivatives? So let me make up an example. This was the kind of thing you saw in the last test, right? And you were happy if there was an equal 0 on the other side because that just meant it was easier, right? And so what I'm saying is if we're going to solve that, and you already know how to solve that in one way, but remember it was a little unsatisfying because it was just guessing, right? We said, what kind of function could I take the derivative of and the second derivative, and yet add them all up and make them equal to 0. And so you should see that, you know, something like tangent, maybe it's tangent of t, you hypothesize. But then you say, well, y prime, derivative of tangent is secant squared. And the derivative of junk squared is 2 times the junk times the derivative of the junk. The derivative of the junk is derivative of secant is secant tangent. And so does it make sense you're going to have a hard time adding those together because they're not like terms? I mean, that formula up there says basically you have this, which is secant squared tangent, and then you're going to subtract 7 of these and add 10 of these. You're not going to be able to add them because they're not like terms. And so, you know, whatever this mysterious function y is, remember y is a function of t, whatever it is, it's probably not tangent. So we said, well, e would be a great choice, right? We just kind of guessed and it worked. And so we said, fine. But with Laplace transforms, we don't have to, you know, have all these different guesses. And then you remember, like, even though we were guessing, we knew it was e to the t, but even then it was really complicated because sometimes it was like, well, is there a double root? Does the answer come out complex? If it's complex, then you have this answer. And if it's a double root, you have that answer. And if they're distinct real roots, you have this answer. And, you know, it's like without the note sheet, we're sort of lost, right? I mean, unless we really put a lot of time and memorization into it. What we're saying here is forget all that. Forget the first couple of chapters where we said, is it separable? When it was like first order, it was separable. Was it separable? Oh, you do this. Oh, no, it's not separable. It's linear. Okay, well, then you got to use the mu thing. We have all these techniques to keep straight. And we're saying, no, we're just going to take the Laplace transform of both sides, and that's going to solve everything. Well, in order to take the Laplace transform of both sides, we're going to have to learn how to take the Laplace transform of a derivative, since that's what a differential equation is. And so let's tackle that conundrum. And then we'll use it to solve that exact problem. You already can solve that, so we'll solve it traditionally. We'll come back to that in a minute. But then we'll solve it using Laplace transform. So you can kind of see, oh yeah, I see what this actually does now. That's kind of cool. Okay, so one, what's the Laplace transform of y? Now, again, it's important to understand, even though I don't need to write that that's a function of t we're talking about there, right? So we're lazy up top in red when I just say y double prime, but we have to know, at least in our mind, even though we're being lazy, that that's some function of t. And again, it doesn't have to be t, it could be x or whatever, but it's like a function of something. So, you know, y is sine of x or y is cotangent squared of x, and we don't know what it is. We're just trying to find some function that will fit that equation up there. So what we're trying to find now is the Laplace transform of a derivative. Now, again, that should feel weird to you because it's like, well, we don't even know what the function is. And so how are we supposed to find the Laplace transform of a function when we don't know what it is, much less when it's the derivative of what we don't know what it is? I mean, this should feel pretty crazy. But based on the definition, can you write it out? Like what's the Laplace transform say to do? I mean, you should say, well, I have no idea where this is going, but I could stall, right? I'm just going to stall and write out what Laplace transforms always are. Whatever junk you are taking the Laplace transform of, always times e to the negative st dt. So now you can't stall anymore because there's nothing else you can write. Now we're going to have to do something with this. Well, notice you're not going to be able to put those together in any way because we haven't even defined what y is yet. We don't know, is this a trig function? Is this e to the x? We don't know what it is. So we can't put them together. So the only choice we have is integration by parts. And the question is this the u and this the v prime, or is this the v prime and this the u? What am I doing? Getting so excited. Is this the v prime and this the u? So I want you to think about that for a second. Well, if we did it this way, then wouldn't u prime be, well, the derivative of that, which I guess then would make it a second derivative. You agree with that? Doesn't that feel like, that's making it worse? And that's actually true. That's actually making it worse. What it's going to be then is we're going to end up with the integral of u prime is, don't we end up with, uv minus the integral of u prime v? Does it make sense if that's sitting there? That's just got worse. Like we don't know how to take the integral with y prime of t. So how are we going to find the integral of y double prime if we can't even do y prime? So that actually turns out to be the wrong choice. What turns out to be the right choice, I'm going to write this out a little more carefully this time, is this is the v prime. Those are all of our ingredients, right? That's what it takes to kind of write out integration by parts. So in this way, if this is v prime and this is y prime, then don't we have to take the integral of v prime to get v? So if I take the integral of that, don't I just get y of t? Now, I still don't know what that is, so it's not like I can take the integral of it. So in one sense, you should say this isn't going anywhere. I'll rewrite it in a second and show you what I mean by that. And then of course, okay, well, if e to the junk, I'm taking its derivative, then it's e to the junk. And then we take the derivative of negative st with respect to t, which means that's negative s. And so isn't that our ingredients? So then we say, all right, this is too hard for us. We're basically saying this is too hard for us. And so in the language of Laplace transforms, let's go transform it to something that's a little easier for us. So integration by parts says, okay, well, if you can't do that, then if you decided this was v prime and this was u, then could you do this instead? uv, which notice is y of t, there's u, and v. I think I wrote them backwards from what I just said, but that's okay, they're multiplied. So there's that, but we don't care about that because we don't have to take the integral of that. And then it's always minus, and then it's the integral of u prime v. So there's the v. Here's the u prime. Notice there's a negative s there. So I'm going to pull that negative s out front just because, remember, we're treating it like a constant. So again, this is sort of hopeful, if you will, because now we're looking at this and saying, have we transformed that into something any easier than before? Was that helpful? Can I now take the integral of this? What are your thoughts on that? Remember, you don't know what it is, right?
Yeah, but that's what we have normally is integral of the yt e to the negative st. So it should be good now.
Now, the issue is we still actually can't do this because remember, we don't know what y of t is. Is it sine of x? Well, then that would be one set of answers. Is it 1? What if y of t was just the function 1 or the function 7? So it's like, how am I supposed to take the integral of that if I don't know what it is? So in one sense, the answer is no, it actually isn't easier. However, would you agree that this whole statement right here is just the Laplace transform of y? The answer is no. You cannot do that. It isn't any easier. And it's because you don't know what function y of t is yet. But that little observation is, if you will, kind of turns out to be kind of genius. And again, that's kind of obvious, but it's like, look back here. Like, isn't this is the Laplace transform of y prime? Well, isn't it y prime times e to the negative st? And so whatever's sitting here multiplied by the rest of this stuff, isn't that what we were taking the Laplace transform of? And so down here, if I have an integral of junk times e to the negative st, then isn't that the Laplace transform of that junk right there? Now, again, you should be thinking, I don't understand how this is helpful, or, you know, what good this is going to do us and so forth, but we'll get
The
there.
y is not prime anymore. So it
It's
might
not
be,
prime anymore, and that's very important. Very important. So in a sense, I'm basically saying, all right, well, let's not do that. So then what we're saying then is we have y of t e to the negative st. But remember, we still have to evaluate that at infinity and 0. Does it make sense? We're not done with that. We actually have to evaluate it at infinity and 0. Remember, it was prescribed to be evaluated from infinity to 0. So we still have to evaluate that. But this over here, we actually don't, because we basically said we can't really do it. So let's just rewrite it back as a Laplace transform and just kind of not do it. So again, the question becomes, all right, what happens to this? Well, you should say, all right, when you put infinity in, don't you get y of t over e to the st? If I put it on the bottom, and since t is infinity, I'll go ahead and write s times infinity, but I could just write infinity, right? E to the infinity. And then it's always minus, and then I would get another y of t, except it would be over e to the s times 0. Now remember, we plugged infinity in for t, so doesn't that actually mean that, you know, these are infinity too? I'm sorry, the first one's infinity, this one's 0. Isn't that true? Like, so the question is, what happens to the one on the left? You know, part of me wants to say, well, doesn't this just become, you know, some number over e to the infinity, which then means it's on its way to 0? That's kind of what we did most of the time yesterday, right?
But if there's an e in that function, then doesn't it go to like 1 or undefined?
Yeah, now let's think about this. This is a Math 253 concept. So if you took Math 253, this will resonate with you more deeply. But what if this function up here was like 3t plus 2, like it was a line? Remember, that's just some function of t. What if it was a line? Who wins from Math 253? If you have 3 times infinity plus 2, where the plus 2 doesn't make any difference, over e to the infinity, which function outruns? Who runs faster, lines or exponentials?
Exponentials.
Exponentials. So this really would be on its way to 0 if that was a line. I mean, just think of something simple like 10, not infinity, but 10. 3 times 10 plus 2, 32. E to the 10th. Bust out my calculator because it's fun. Second e raised to the 10th. Whoa, 22,000. So the top is 32 and the bottom is 22,000, and I've only stuck in 10 for t. I'm not a long ways from infinity. So if that function on the top was a line, great, that whole thing would go to 0. What if that function on top was, you know, like a parabola? 3 times infinity, but now infinity is being squared. Do exponentials still outrun parabolas? Math 253 people?
Yeah, they should. The e to the infinity will still be bigger.
Yep. E to the infinity is still bigger. Exponentials are bigger than all polynomials. That could even be t to the 20th. In other words, the basic concept is if you had 50 to the 20th power or e to the 20th power, is that right? No, 50th. Because like the base up here is the t. So it's t, but we're making it 20 instead of, so this would be e to the 50th. 50 to the 20th power is a big number, but e to the 50th gets bigger. Like it still wins. Parabolas or any polynomial gets outrun or is outrun by any exponential. Now, are there functions I could stick up there though that would give E a fight? What function would give it a fight? Well, wouldn't E? Like, what if it fought itself? Down here, we had E to the S times infinity, right? What if on the top, this was E to the AT? What if it was also E? Except for, again, isn't T going to infinity? Now, does it go to 0? The answer is not necessarily.
Should it go to 1?
Yeah, like if A and S were the same, doesn't it feel like it's a fight? It's a fair fight. Doesn't it feel like it might go to 1 now? But let's play with that for just a second. Again, you don't have to know this, but for those of you that are more proofy, and by the way, what I'm doing here is what I like to call a poof. It's not kind of a form. I'm not writing it down real formally. We're just reasoning and playing with it so that you kind of see the idea. Let me give you a simpler example. What if you had like E to the 4x over E to the 5x, and we're going to let X, and I'll write this formally. We're going to see what happens as X goes to infinity. In other words, as X gets bigger and bigger and bigger. So the top is slightly smaller than the bottom, right? So the question is that going to go to 1? Because it's basically, you know, part of me wants to say it's basically E to the infinity over E to the infinity. So therefore it's 1. But then, like, does it matter there's a 5 on the bottom and a 4 on the top? You know, or what if I switched them? There was a 5 on the top and the 4 on the bottom. You know, again, do you have Math 253 is what gives you the skill to actually deal with this. But fortunately, I can do this just with your algebra knowledge. Isn't E to the 4x possible to write as E to the x to the 4th? Isn't that how exponent rules work? And isn't on the bottom then that E to the x to the 5th? Now, what do you think that goes to? Do you see that as any different? Do you understand that E to the x to the 4th is really just this? Again, I like to write stuff in stupidly simple forms because it's not, that stuff isn't that complicated. Isn't that what you have? Isn't that what that means? All right, do the algebra. What does that reduce to?
1 over E to the X.
Bonk, 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 bonk. 1 over E to the x. So what happens to that as X gets bigger?
Goes to 0.
It is going to 0. So this is going to 0. Do you see that? Now, what happens though if I flip it upside down? Or what if I screw with it a little bit? I'll take this back, but what if this is a 6? Does it go to 0 now?
Goes to infinity.
It goes to infinity. It diverges. And so this term, we were used to yesterday, you know, this term going to 0, right? Like that part of the term right there went to 0. That's why, that's the brilliance of Laplace choosing negative s, because it moved E down to the bottom, and then as T got large, that would make that go to 0. But this won't go to 0 unless, as you see right here, this will go to 0 if and only if A is less than S, or I could say S is greater than A. Does that make sense? Now, wasn't that something we said yesterday too? Didn't we say that, you know, for E, can I still pull that up? I'll just pull that up from yesterday really quick because I think I can find it fast. Didn't we yesterday say, yeah, this turns into this, but only if S is bigger than A? Like, that's not the first time we've seen this. And so again, that's a technical point. It's kind of like saying, what's the square root of X squared? You know, the answer to that is not X. It's the absolute value of X. There's kind of a technicality to it. And that's kind of true here too. Now, the cool thing is we aren't going to leave this in the land of S. We're going to take it back out and put it back into T again later. And so in some respects, these little caveats that we're adding, we don't even have to keep track of because we're going to take it out of the land of S anyway. But basically, as long as that function, that y, for almost any function you would pick for this, right, for that y of t, whatever function you want to pick there, that's still going to go to 0. So this is going to go to 0. But it's not as obvious as it might seem. And by the way, and your book won't tell you this, and if you read this section in your book, you'll think, wow, this is almost unintelligible. I don't understand what they're saying. I'm trying to explain this to you in a lot simpler way. There is one exception. Does anybody remember from at least my class in 253? What function outruns an exponential? There was one in that limit business that we did.
Is it a factorial?
That's exactly right, Connor. Factorial. So in a sense, that would be another limitation to this. If that y function was a factorial, then that would not go to 0. It would actually go to infinity. And that'd be really important. So that sort of means, what that means practically is you're never going to see factorial in any of these problems because that would kind of screw this up. Not only that, it turns out the derivative of a factorial is really a weird, nasty problem anyway, and you've never really played with those much. So basically, we can say this is on its way to 0 with a few, theoretical caveats that are actually pretty important. But then what happens over here to the second part? Well, notice when you put 0 into your function right here, you're like, who knows what'll happen for that? Like, what if it was t squared plus 3? Well, then wouldn't it be 3 if t was 0? Or what if it was e to the 2x? Well, then wouldn't it be 1? This is not going to be 0. Do you understand this? This is not equal to 0. Like, it is literally whatever you get when you put 0 into whatever that function is. As I said before, if that function was 3t plus 2, then when you put 0 in, you get 2. And so there's lots of examples of functions where you're not going to just get 0 every single time. However, what happens on the bottom? What's e to the s times 0 since s is a constant?
1.
1. So what do we actually get then for all of this? Basically, this whole thing here, I'll just write this out. Hence, this whole thing is really negative y of 0. Since the bottom is a 1, like there's the negative, here's y evaluated at 0, the bottom is just a 1, so it's really just minus y of 0.
Followed by a bunch of ifs and only ifs, right?
Yeah, followed by these little kind of caveats. And the cool thing is as I said, we won't really have to pay any attention to this because all functions that we've been choosing, like sine, if we choose sine, then this function goes to 0. Because the bottom gets huge and all the sine does is vacillate back and forth between 1 and -1. Even if it's multiplied by 10, it vacillates from 10 to -10. So this will go to 0 if that's a sine function. It goes to 0 if this is any polynomial, even t to the 20th power, e is going to outrun it. It will go to 0. The exception is if this is an e function, we need the exponent that goes with e to be bigger than whatever s is. But again, we won't even have to worry about that because we're going to change it back into t anyway. And then it can't be factorial. So what's kind of the big conclusion for this that you really need to kind of lock away? The Laplace transform of y prime, and I think this is a place where I need to kind of remind us that that's t, is actually equal to negative, let's see which way I want to write this. Who cares? We'll change it later. Negative, what did we just say? Y of 0. In other words, 0 in the function, and then plus s times the Laplace transform of y. Now, again, that should feel like, why is this helpful? Or like, how can that help me? How can that help me do anything? It should feel like that can't help me do anything. I don't find myself liking minus signs in the front, so I can't bear it. It's got to go over there. I'm going to write it the other way. So this is huge. This is really important. If I could set off dynamite around that, I would set it off. Let's take a look at my cheat sheet. Thug's table of Laplace transforms. Where be this? There it is. Is that what we just said? Does it bother you that I, instead of saying y of t, I just said f? It's a function, right? Y of t is some function of y. Here, though, I was a little lazy. I didn't say f prime of t. I just said some function. Laplace transform of a function's derivative is s times the Laplace transform of the function without a derivative minus the function evaluated at 0. So that's huge. That's important. Now let's go make the second one down here. Because didn't we have second order derivatives? And we even had thirds occasionally, but let's try to figure out that second one then.
It bothers me more that I'm going to have to do one more integral than I thought I was going to have to do.
No, one of the cool things about this is you don't have to do any integrals. That's what's cool about Laplace transforms. I'll show you what I mean by that in a little bit.
Okay, yeah, I was going to say.
Because right now, although we wrote out what this is, you should still kind of say, well, yeah, but what is that? You know, like, it's kind of like I still have to, I guess that's saying I still have to take the Laplace transform of whatever the function was. I mean, maybe that's what you're getting at, Connor. So what about the Laplace transform of, and this time I will be a little lazier and just say y double prime instead of y double prime of t? Well, that's not hard. It's, well, didn't we just say this? We said it's the Laplace transform is always the same. Isn't this what it is? So then we take the same approach we just took a second ago, which is we say, well, I'm going to need v prime to be the y double prime so that I can take the integral of v prime and get v, and the integral of y double prime would be y prime, right? Fundamental theorem of calculus, derivatives and integrals are inverse operations. And so I'm purposely picking the other function, the e to the negative, just like we did before. The e to the negative st is our u, which makes our u prime negative s e to the negative st. So then what do we say that thing becomes? Fortunately, this isn't that bad. So then we say, okay, well, cool. Then what is that equal to? It's equal to u times b. So that's y prime, and I am going to write the t in here, y prime of t actually, times e to the negative st. And again, we have to evaluate that from infinity to 0. And then it's always minus u minus the integral of u v prime. I'm sorry, u prime v. U prime v, so v is y prime, and u prime is negative s e to the negative st, but then let's pull that negative s out front again. Okay, so in the same way then, what happens to this? I'm not going to rewrite this whole thing out because we just did this a second ago, but when you put infinity in, it's going to go to 0. But when you put 0 in, you're going to get minus y prime of 0. Like that's what's going to be left of that when you evaluate that. Do you agree with that? And then over here, don't we say, hey, isn't this just the Laplace transform of y prime, which we just figured out a second ago, by the way. So it's plus s times the Laplace transform of y prime, but we know what that is. we know what the Laplace transform of y prime is. So what's the Laplace transform of y double prime? It's equal to those last two blue statements. So negative y prime of 0 plus s times, well, we just figured out what that was a second ago. It's right up there. Laplace transform of y prime was s times the Laplace transform of y minus y of 0. So what does that all become? Here's the final $1 million statement. The Laplace transform of y double prime, and maybe I'll put the t back in, is equal to, multiply this out, that's s squared times the Laplace transform of y. And then s times that statement is minus s times y of 0. And then this statement up here that I ignored until now, which is minus y prime of 0. There's the Laplace transform of the second derivative. Now, I'd like you to look at that for a pattern for a second. Like, what do you notice about the s's in those three terms? This is what mathematicians are all about, is patterns. What do you notice about the s's?
They're quadratic in nature.
Yeah, so it's like it started as a squared, right? And remember, that's kind of how we viewed that y double prime there, is like the second derivative. And so it started with two s's and then went to one s, and then it went to no s's. It's almost like this is s squared, this is s to the first, and that's s to the 0. Does that make sense? What do you notice about the, and this is far less obvious, what do you notice about these statements? This, and this. There's a pattern to that too. Don't forget, Laplace transform is just an integral.
So the derivatives are increasing in towards the right.
That's actually pretty good, what Connor just said. In other words, if this was an integral, if you took the derivative of an integral, doesn't that take it away? And now there's like no derivative at all. So it's kind of like you took a derivative going this direction, and then you did it again. Like you're taking derivatives as you move to the right, and you're decreasing the s's as you move to the right. That turns out to be a really cool pattern, which basically means we could now answer the question, what's the Laplace transform of y triple prime in the event that we had a third order differential equation, which we really won't, but we might have one here and there. But what would that be then? Well, let's just reason this out based on pattern. This was to the second, and this started at the second. So this is to the third, so it's going to start at the third. So this is going to have an s to the third, and then an s squared, and then an s to the first, and then an s to the 0, which is really just a 1. So maybe I'll leave that there, but we'll change it to 1 later on. And then what do you notice by pattern? Well, notice it always started with, and do you notice the pattern works up here, by the way? See how it's s to the first, and then s to the 0, and then it's an integral. And then if you take the integral, now it's a derivative of that integral. Like it's, you see how it's the pattern works up there too? But notice it always starts with just a Laplace transform of y, no matter what it is. Isn't that what this started with? Just a Laplace transform of y. So that's what it always starts at. So this is going to be times the Laplace transform of your, just your y function, not y cubed, not y to the, not the second derivative, not the first derivative. And then what about the signs? We didn't pay attention to that. Are these pluses or minus signs? What do you see as the pattern there?
Looks like it's always negative.
Yeah, the first one is positive, and then they're all negative after that. So this is minus s squared. If I take the integral, if I take the derivative of the integral of y, then I just get y. If I take the derivative of y, I get y prime. If I take the derivative of y prime, I get y double prime. And those are minus signs. What else is missing by pattern? It's not just y. What is it?
Y of 0.
Yeah, you're evaluating these at 0 every time. So by pattern, that, which is awesome. I mean, can you imagine how much time that would have taken to kind of make that for ourselves? If you want to really get this, you might do it. It's not that terrible. In other words, isn't the Laplace transform of y triple prime the integral of y triple prime e to the negative st? And if you do what we did before, which is say that's my v prime and that's my u, then aren't you going to end up with some gobbledygook and then the integral of y double prime? And then you can say, oh, look, that's the Laplace transform of y double prime. And I know y double prime's Laplace transform. I just did that a second ago. Like, you could slow down and make that one more time, kind of convince yourself that that pattern that I'm telling you, that I'm showing you, is actually going to persist. In the interest of time, I'm showing you that. I guess you could say a little prematurely, perhaps. Let's take a look at my note sheet. So first of all, do you agree that's what we just got for the second order derivative? Started with s squared, and then it went s to the first and s to the nothing. And then we had Laplace transform of f, its derivative is f, its derivative is f prime, always minus signs, always evaluated at 0. Do you see that pattern here? Isn't that what we just said? Again, I'm using f here for function instead of y for function, but it's the same logic. Again, slow down, s cubed, s squared, s to the first, s to the 0th. Integral f prime, f double prime, minus, 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 always 0, 0, 0. Again, you should have a sense of why is that we evaluated at 0? Because we evaluated the integral from infinity to 0. And the only thing that survived that was the 0. The infinity made it go to 0, but we actually had to evaluate that thing at 0. Now, your brain should be, a little bit spinning, but but the good news is we're kind of there now. Like, you actually, other than some practice, you actually know everything you need to know to do everything we need to do. You got to be good at algebra, and we'll kind of talk about that as it comes along. But let's actually go back now. Now that we know this, let me show you how we can use all of this stuff we've built to go tackle, well, that equation right there. Does it make sense? You can now take the Laplace transform of both sides of that, which you couldn't do before. And again, your book does not do this. Like, your book, all today is just properties, and I'm showing you what 7.3 was in the book for the most part here. And then 7.4, which you may have noticed in the syllabus where I'm going to cover, is also preparatory knowledge. And then finally, Tuesday or Wednesday next week, I would show you, the book would show you this. But I just feel like I've shown you so many esoteric and theoretical things, you should kind of be feeling like I don't understand what all this can do. And I just think I can't wait anymore to show you that, or you're just not going to start to take in the power of what this really is. So that's why I want to immediately do that right now. So let's title this. Okay. So what? Who cares? What does this do? Now let's first quickly solve this cheating. We used to cheat by sort of guessing that our function y must be e raised to some power. So maybe it's e to the 5t, maybe it's e to the 7t. And so you may remember and I'll kind of quickly rebuild this from the start. So we lamely guessed, again, that's one of the advantages of Laplace transforms, is we don't have to guess. So we guessed this answer as being possible, and then we kind of plugged it in, and this is what we saw. So we said, well, okay, well, I'm going to need y prime and y double prime. So y prime would be r e to the rt. Y double prime would be r squared e to the rt, as you know. And so then if I plug that stuff in, Then I get r squared e to the rt minus 7r e to the rt plus 10 e to the rt equals 0. And then we were basically saying, you know, is there some way we could figure out what r is that would actually make that be 0? And so then we noticed, hey, look, every one of them has an e to the rt in it. So if I take that out, and for some of you, although I showed you this at the time and you survived the test, maybe me showing you this a second time is like, oh, now I see where that came from. Like I'm in a position to actually take that in. So now we're sitting here with, hey, look, junk times junk equals 0. And e to the rt will never be 0, no matter what you pick for r. But r squared minus 7r plus 10 could be. And that's the auxiliary equation idea. So we just looked up here, we got to the place, and some of you did this without understanding. You just kind of did it and saw that it worked and really never felt that good about it. We just said, hey, look, this is junk, well, squared, because that's, you know, a second derivative, and 7 times r to the first plus 10 times nothing, just 10. So then we solved this and we said, hey, that factors to r minus 5 and r minus 2. So that means r is 5 and r is 2. And then we said, hey, those are distinct real roots, so I don't have to do anything fancy. Remember, there was all these little stupid tricks and stuff we had to pay attention to. This one is easy. And so we say, cool, that means I think I know what y is. Y is a function of t is, we saw that any constant times e to the 5t plus any other constant times e to the 2t, not rt. Like that was our really cool general solution to this. So we saw that those aren't two separate solutions like we first thought. It has two answers. No, it actually just has one huge answer that includes both of them. And remember, C1 and C2 can be anything, and that will actually be true. So that was our answer. Now, that's actually not terrible. I mean, if you're okay with guessing and you're okay with all of the caveats of, you know, double roots and imaginary answers and all that kind of stuff, that wasn't that terrible. And as I've told you, as I've hinted at, Laplace transforms are cool in the sense that we don't have to guess anymore, but there's still a lot of work. It's not like this, it's not like suddenly now everything is easy. The only good thing about them is you don't have to guess and it just works in every situation. That's what's really cool, but you got to be an algebra stud for it to work. Now let's see if we can get the same exact answer using the idea of a Laplace transform. So, old way. Now, the Laplace way. By the way, anybody see the old sitcom, Laverne and Shirley? That was Laverne's L. I don't know how you saw that. If you have, you guys are way too young for that. But. The Laplace way. Now, what appeals to me about this is, as I mentioned before, it's the algebraic idea that I'm just going to do the same thing to both sides. So I'm just going to walk up to that equation, and I'm very troubled by the fact, and this is so neat, I'm very troubled by the fact that it's like, well, this is a second derivative, and that's a first derivative, and that's no derivative at all, and it's like I can't add them together, right? That was the problem. That's why we made the guess we made, and we said it can't be tangent. But I'm really comfortable this far into math, and so are you, with the idea that in algebra, we do the same thing to both sides, and that's totally okay. So that's exactly what we're going to start with here. We're going to take the Laplace transform of both sides. Now, here's what's kind of cool. Watch what that does. This is what's kind of neat. So let's see. I think I'll write this out. We don't really need to be in a rush. I think I'll copy this. So we already figured this out a second ago. We already know the Laplace transform of y double prime. So rather than rewrite the whole thing, let's just steal it. But I am going to kind of write it out down here. Get rid of some of this other stuff. So there's the Laplace transform. Maybe I'll get rid of the t's just since I didn't have a t in my. So there's the Laplace transform of y double prime. What about minus 7? what about when we take the Laplace transform of -7y prime? What did we say we can do with that -7?
You can factor it out, right?
Yeah, again, think of the integral. It's the integral of -7y prime. Well, the integral of -7, you could just pull the -7 out front. So in other words, we say, I can just leave the -7 out and just multiply that by whatever the Laplace transform of y prime is. So we would say, let's see, what was it? It was s times the Laplace transform of y. So that'd be -7s Laplace transform of y. And then it was minus y of 0, right? Except for we're multiplying that by -7. So now that actually becomes +7 y of 0. Is that right? Did I get that right? Let's just double check. So I'm basically taking this whole thing times -7. Did I get that right? -7s Laplace transform of y plus 7 y of 0. Yeah, I got it right. So the fact that I had to multiply it by -7 was, something to consider. It wasn't like that was just nothing. And then finally, what's the Laplace transform of, well, just 10y? Well, it's just 10 times the Laplace transform of y. But I want you to notice what this accomplished. If I go back and kind of draw, like I'm going to add all these together now, right? Like I'm going to add this together with this and this. What do you notice about what you have left behind now, though? That's kind of cool. Remember what happened before when we were trying to add this? We sort of said, well, you can't add those. That's y double prime, y prime, and y. Those are different animals. I can't add those together. But what do you notice a Laplace transform did so that when you try to add these together, what's going to happen now? What do you notice about them?
You have some similar, very ugly animals.
They're still ugly, but they're duck-billed platypuses, but there's only one now. It's like Laplace transform of y. It actually reduced, Laplace transform basically took away the second derivative and the first derivative. It's like all you have is Laplace. You have a constant in front, but a Laplace transform of y, Laplace transform of y, Laplace. You can actually add them. You see what I mean? You can actually add these now, whereas you couldn't add them before. That's kind of one of the beauties of this. So let's add them. What do you get? Well, notice you have a Laplace transform of y, and in the top equation you have an s squared, and in the middle equation you have a -7s, and in the bottom equation you have a 10. Isn't that just distributive law? In other words, I'm just adding this, this, and this since they're all like terms. So, this is a multiplication sign. It's really, I just factored Laplace transform of y out of all of those.
There's the auxiliary equation.
Yeah, isn't that the auxiliary equation? So that's kind of cool. In a sense, that sort of feels like maybe that's a shortcut. Like I don't think that's a coincidence that just showed up there. And let's see, what have I left out? Well, let's just kind of write all the other junk down there. So I have a minus s y of 0. I have a plus 7 y of 0. And then I have a minus y prime of 0, right? And wait, what is all that equal to? What did I say I was going to do right here? Laplace
It's going to be equal to
transform
0.
both sides. So that means I got to take the Laplace transform of 0. I've never thought about that before. What's the Laplace transform of 0? Again, you think about that for a second. I'll probably erase this. Well, maybe I won't.
I think it'd be 0 because you'd have 0 over s.
Wouldn't it be a constant? since you're integrating 0 and the derivative of a constant is 0?
All excellent points. I want you to think about that. Well, again, you don't have to know much to at least write this down, right? That's the Laplace transform of 0, isn't it? All right, we'll take the integral. What do you get? Now, I like both of the points people said were really good. One person was like, well, isn't it 0 because it's 0? But then David pointed out, well, isn't the integral of 0 a constant, since the derivative of a constant is 0? So wouldn't that be a constant? And so like maybe it isn't 0. Like, give you a second to think about it. My bagel's getting cold. I'm gonna give you 10 seconds to think about it.
Asking Landon.
Anybody have any strong feelings now?
Doug, I'm gonna have a strong feeling in just a second. I'm just waiting on something, okay? I'm real close though.
I feel a feeling coming on me, says Connor.
Well, maybe if you're taking, because you're doing it from 0 to infinity, you're going like the constant minus the constant. So does it actually equal 0?
Yeah, that's an interesting
You
thought.
would get a constant, but then you'd subtract it. I'm not sure.
So 0 times anything is 0. So this really does reduce to that, right? Like you don't, the e to the negative st is gone because you're multiplying it by 0, right? And this is what Ben is saying, and kind of David. The derivative of a constant is 0. So the idea that the answer to this could be 7 or any constant. And then I have to evaluate that at infinity and at 0 and subtract. That's what Ben is saying. It's all true. What happens when you plug in infinity and 0 and subtract?
You get 0. You get 7 minus 7.
What do you notice? What do you plug? Where do you plug infinity and 0 into?
Nowhere.
Nowhere, because there's no t's. Does that make sense? So when you plug infinity in, you get 7. I mean, isn't that the definition of y equals 7? Like no matter what you plug in for x, you get out 7. So this ends up, when you plug infinity in, you get 7. When you plug 0 in, you get 7. You subtract those. It is 0. Now, logically, remember what an integral actually is. Conceptually, what is an integral telling you? If I say, what's the integral of 3x plus 2? What is
Area
it?
under the curve.
Area under the curve. If I say, what is the area under the curve? Y equals 0. Isn't this the line y equals 0? And remember, under the curve means between the curve and the x-axis. And so isn't there no area? I don't care how far you go. If you go from 0 clear out to infinity, there's still no area there. So fortunately for us, yeah, the Laplace transform of 0 is actually 0, which is great. But again, notice you don't have to be told that. I could have just told you and moved on. I could have said, and I think most teachers would do this. This is the kind of the up and the downside of the way I teach. They could have just said, I could have just said that in the Laplace transform of 0, because the integral of 0 is 0, and then I took 2 seconds and went on. But it's like, that's not obvious. Like you got to think about that a little bit. I just think it feels good to me to go, yeah, I completely understand that the Laplace transform of 0 would be 0. I hope you do too. Okay, so what that means is, bam, all of this is actually equal to 0. Now you should say, okay, great, but I don't understand how that helps me do anything. So, watch this. Let's continue. And here's the algebra part, or the brilliant part, or maybe what would never occur to you. Let's see. So I have the Laplace transform of y multiplied by my what turned out to be the auxiliary equation. And now I'm going to add all that other junk to the other side. So it's a negative sy0. So s. So if I add it to the other side, it'd be s times y of 0, but it'd be positive, right? And then if I subtract 7 y of 0 over there, I get this. And if I add y prime of 0 over there, I get this. Does that make sense?
Doug, is it supposed to be y prime, y double prime? Minus 7y prime.
I don't know. Did I make any mistakes there? No, because our second derivative, our Laplace transform of our second derivative only had a y prime. So no.
Okay. So we have just two regular y's.
Yeah, two regular y's. That's right. And that's
Can we
because
combine those like terms, or?
yeah, we could. So in other words, our Laplace transform of our second derivative had a y value, right? Had just a y of 0. But then didn't our y prime also just have a y of 0? So there's like a couple of those. Yeah,
That makes
good.
sense. Okay.
I love that. You're
Hunter's
thinking.
trying to keep that pattern intact.
Well, I'm looking at it, I'm
Exactly.
like, what is
Yeah.
going on, man? I feel so lost.
Yeah, you're a pattern-seeking creature, and so you're thinking, what is that? Now
Well, I
let's
guess-
think about what these were. Y of 0 and y prime of 0. Like I don't really know what to do with those. Let's just leave that for a second. And S's and 5s look the same a lot, so I got to be a little more careful with my S's. So yeah, that's kind of a weird looking gobbledygook. But one of the things I want you to think about is, weren't these the initial conditions that were given on your test? Like, didn't I tell you y of 0 was 6 and y prime of 0 was 12? You know, that kind of a thing. So just to make this go a little nicer, let's kind of go back and let's go back and do that. Let's see. What if I said, let's try to make this really, let's make this really easy, just to make it come out nice. Let's give the initial conditions y of 0 equals 0 and y prime of 0 equals 0. Now I could say they're equal to 12 or 7 or anything else. Actually, let's mess with one of them. Let's make this one 8. So we'll say the original slope is 0, but y of 0 is 8. And of course, now that we know that, does it make sense we'd be able to come up with values for these? C1 and C2? Let's see, should I do that really fast? Let's see, if y of 0 was 8, then that'd be 8 equals C1 plus C2, wouldn't it? If t was 0. You agree with that?
Yep.
And y prime, of course, would be equal to 5c1 e to the 5t plus 2c2 e to the 2t. And so if y prime of 0 was 0, then we'd have to say 0 equals 5c1 plus 2c2. You agree with that? So we have two equations, two unknowns, and because maybe I'll cheat and make this, let's make this work out. Let's make this work out nice. Like I'm gonna fix this answer. So let me just make this work nice so we get nice whole numbers. This is what I did to make your test work out, by the way. Did you notice? Hey, everything worked out wonderful in the test. So let's see, we've got to make 5c1 plus 2c2 be 0. Does it make sense we could do that if we chose c2 to be 5, which makes that 10, and c1 to be -2? Does it make sense that would make the bottom one 0? But if I then go back up here and I put c2 as 5 and c2 is 5 and c1 is -2, then this would need to be not equal to 8, but equal to 3. I'm doing this for you future teachers. There, I just made a problem that came up really nice. I don't know if I should have done that from the start. So now we actually have a particular solution based on our 2 initial conditions. So since that's, usually the case, I mean, you really are trying to model something, right? Where did it go? I copied it down there and then it disappeared. It's gone. Oh, it's right there. So if we copy that same logic down here, does it make sense that will make our world a little better? I don't think you're seeing anything right now because it looks like my screen's black, but that's okay. We'll be back in a second. Duplicate. So if y of 0 is 3, then isn't this become 3s minus 7 times 3, which is minus 21, and then y prime of 0 is 0. So do you agree that that's what I have now? You okay?
Yeah, it looks good.
Okay, so then I could say the Laplace transform of y, which we still don't really understand how to do, right? But then wouldn't that be equal to 3s minus 21 over s squared minus 7s plus 10? Like if I divided it over?
Hey, Doug, out of curiosity, are we still using our kind of guess of like C1 3RT plus C2 3RT?
No, that's what's cool about this is we've made no such guesses. You understand that?
Kinda. I feel like when we used the equation, we were going back to guessing a little bit or to using. I guess I thought we were done with that equation. So does that make sense? When we plug back into that C1 e to the RT plus C2 e to the RT to get these values?
He was doing that to get nice numbers.
I just did that to get nice numbers. In other words,
okay.
that produced C1 and C2 being -2 and 5. And so these initial guesses is all I did was play with those initial guesses until it gave me good values for C1 and C2. But then I skipped all that and just copied it down there. So no, we have no idea right now that the answer is E. For all we know, it's still sine or cosine or any, we have no idea. There's no guessing involved. That's what's so powerful about this.
Okay, I'm back with you. Sorry about that.
That's awesome. That's a wonderful question. Now, notice it says Laplace transform of y equals junk. Well, here's where the table that we've been working on comes in. In other words, if I look back at this table, and we've built a lot of this table now, let me get rid of my hatchings on it. Cut. If we can find something that looks like that, because isn't that what this is saying? Like, notice this says the Laplace transform of, well, 1. In other words, if the right side of that had said 1 over s, we would have went, oh, wow, that's Laplace. Our function is 1. The answer is 1 because the other side is 1 over s. And so there's our y. There's our y value. It's 1. Or we say, no, that's not what's on the other side. It's 1 over s squared. Oh, okay, well, then our answer is t. Remember, we're trying to find y. This is all we have to do now is get the right side to look like what we see in this table. So So we're almost there, but it just takes a little bit of algebra. Now that's a little messy, so let's go work on that. So let's see, would you agree that, and because I know where I'm going with this, you don't, but I know where I'm going with this, so I'll be better at this than you would be. But I do notice that the bottom factors to s minus 2 and s minus 5.